Everybody, very welcome to our webinar. This is webinar number 6, and it will be about regulation today. We are talking about the project, European project called Integrated 4D Driver Model. And these are the partners that you see here on the screen. The project number and all the details are given here. If you go to the next slide, so I go to the objective and vision of the project. So what is the vision of this project? We want to lay the foundation for a new industry standard methodology to establish a credible and realistic human driver model, so that we can virtually assess the human driver when we are talking about connected, cooperative, autonomous driving systems. And the objective is the delivery of a library of credible models of heterogeneous human driver behavior. Then this model will serve as standardized multi-objective evaluation framework, which is adaptable to application ranging from safety assessment of an automated driving system to insurance risk evaluation. Okay, in the next slide, you see the connection between the different work packages. You see that the first work package was just gathering the evidence of the human factors, and then this was passed to the different other work packages for the mapping of the human factors, for crafting the robust 4D human driver models, to evaluate the 4D human driver models in real world field experiments, and everything then is integrated into encoding the driver heterogeneity into models, and these models are used, you see work package 6, where different applications are evaluated to see how this model is performing in real applications. Yes, and there you see in the next slide what is the series of webinars that we have prepared. Today is the webinar number 6. There you have also the registration links for the coming webinars, and you have also here the QR code where you can also directly register from your mobile phone or computer. So we're looking forward to give you this webinar, and these are the speakers today. Cut-in scenario regulation. So we are basically going to summarize the reliability of human reference models according to United Nations Regulation number 157. And it is the second part of the webinar go in direction Augmented Human Driver Enhanced Model. So in the first part, Giovanni will talk about the UN regulation human reference model, then how one can learn for professional drivers in safety critical cut-ins. And then me and Kranthi will continue with the augmented human driver model, and this will be based on the behavior of vehicles, and we integrate also uncertainties and show you how this can be used for validation and verification based on the data available from the Joint Research Center of the European Commission. But we come to that first. We give the floor to Giovanni, and just as a reminder to everybody, if you want to ask questions, please use the chat, put all the questions in the chat. So at the very end, we will collect all these questions and we answer jointly, or everybody according to the question. We'll give you answer to what you were wondering about the presentation. So we are looking forward to this and see you. We start with Giovanni.
Thank you, Galia. Thank you for the floor. I start sharing my screen so I can share my presentation. Okay. Perfect. So as Galia was saying, what I will do is I will speak about how much reliable are the models proposed in the Regulation 157, and then I will show you the results, the evidence of the comparison between the output of these models and the empirical data that we collected in an experimental campaign that we conducted last year, an experimental campaign that concerned emergency cut-in maneuvers. So let me just start introducing you the concept of cut-in maneuver. I know that most of you are already familiar with this concept, but just to refresh your mind, a cut-in maneuver is an event like this. So it's an event where basically you have a vehicle in front of you that suddenly changes the lane and enters your trajectory. As you can imagine, since it's a sudden event, it can be very risky in particular situations, in particular conditions. And indeed, just to give you some data, 17% of the crashes are linked to this sudden lane change maneuver. Why? Because they are unexpected, so they are difficult to handle, and they require that the driver is attentive in order to prevent the crash. So,
Giovanni, can you come a little bit closer to the microphone? Yes.
Yes.
Thank you.
I have my earphones, so I hope you can hear me well.
Yes.
Otherwise, I can raise my voice. So, as I was saying, the cut-in maneuvers are difficult to handle, especially in some cases, especially for human drivers, the critical safety cut-in maneuvers. So we expect that with the automated driving, we will improve such situation. Why? Because in theory, an automated driver is always attentive, so we do not have distracted technology. In theory, the skills of an automated driver should be better than the skills of a driver. So, for instance, the reaction time of autonomous vehicles is expected to be way shorter, not zero, but almost zero, is expected to be very close to zero with respect to human drivers. And then another way the autonomous vehicles have to handle the cut-in situations is the connectivity. Because since we expect automated vehicles being connected among each other, connectivity gives you the possibility of coordinate the maneuver. So instead, we do not have sudden lane changes anymore, but we have a vehicle that communicates with the other one saying, look, I'm about to change the lane. However, even if the automation is out there, some rules must be defined also for automated vehicles because the cut-in remains a critical situation. As you can see, it's not always taken by granted the fact that an autonomous vehicles and autonomous technology can handle this situation. So this is why we are developing and people are developing regulations. So the UN Regulation 157 is the first global regulation on the type approval of automated driving system. It has been adopted in 2021, and it concerns several traffic scenarios, among which we have critical emergency cut-ins. The general idea behind this regulation is that an ADS must be at least as safe as a human driver. This is the core idea of the regulation. And what is the goal of the regulation, given this idea, is to provide a benchmark model that mimics the short-term longitudinal behavior of a driver reacting to a cut-in maneuver. So for this reason, the regulation proposes two models to mimic this behavior. But the idea is to mimic the behavior of a human driver. But now you may wonder, which human driver? Well, the idea is to mimic the behavior of a competent and careful human driver. Competent and careful human driver means a driver which is competent, so he or she knows how to drive well, and is careful, so it's attentive, is not distracted, and is attentive, in this case, to avoid a cut-in crash. In particular, the models proposed in the regulations, there are two models proposed in the regulation, and they provide the so-called collision boundary of a competent and careful driver. So these models, what these models do is to distinguish between preventable scenarios, so scenarios according which a human driver is expected, a competent and careful human driver is expected to avoid an accident, from unpreventable scenarios. So those scenarios, those cut-in maneuvers, those characteristics are so risky, so extreme, that even a competent and careful human driver cannot avoid the accident. Now, just let me give you a practical idea of what is this collision boundary. For instance, you can see here this figure. This is a figure taken from the regulation, so you can check it. I included several figures from the regulation. This is a figure in which you have on the x-axis the longitudinal distance. The x is the longitudinal distance when the maneuver, this cut-in vehicle, starts entering the trajectory of this other vehicle. On the y-axis, you have the lateral speed, so the maximum lateral speed of this vehicle while doing this movement. Well, depending on this, on the combination of these two characteristics, the level of safety of the maneuver varies. And the output, the goal of the models proposed in the regulation is to distinguish these events between preventable for a human driver from those who are unpreventable for the human driver. For instance, these green points, this green region is the preventable region. So we expect that the human driver, we expect that the human driver is capable to avoid the crash in this region with this longitude, with the cut-in maneuver happening at this longitudinal distance with this lateral velocity, while this red region is the unpreventable region. So even a competent and careful human driver cannot avoid the accident. This is the output of the models. No, this is why the models are included in the regulation. Instead, this orange region is the region in which we have the models say that the competent and careful driving will face with an accident, but not a longitudinal one, but a lateral one. So this vehicle hits the side of this other vehicle, while this yellow region is the region in which we do not see a crash, not because the situation is safe and is safely handled by the human driver, but because the driver overtakes this other vehicle before this vehicle completely entered the trajectory. So this is just to give you an idea of what these models do in the regulation. As I said, there are two models proposed in the regulation. The first is the competent and careful model. Name is direct, it's simple. It's known also as the Japanese model because it has been developed by Japanese colleagues. And the output of this CC model, the outputs are two. The first output is the precise time instant when the driver, the competent, careful human driver, starts reacting. What does it mean is the instant when the driver, facing an emergency, a critical cut-in, starts lifting the foot from the accelerator pedal to start braking. This time instant. The second output of the model is the braking profile. Is the braking profile of the driver to reach the maximum deceleration and avoiding the crash. These two figures are taken from the regulation and explain the logic behind this model. In particular, the figure on the left tells you how the time instant is defined, because the idea is that you have this model, which is replicated by the behavior of a driver here is replicated by the model, facing with the cut-in coming from this vehicle. This vehicle can wander, can oscillate inside the lane, but then if this vehicle exits this wandering zone, we can assume the model assumes that the cut-in is about to start. And then after a perception time, the driver reacts to this cut-in. How? With a delay, a perceiving delay of 0.75 seconds. This is what the CC model does, replicates. Okay. This is instead on the left, on the right, sorry, we have the figure that gives you more insights into the braking, how the braking behavior is defined. So we have the perception window, after which we have the delay decision, the braking decision with a certain delay, after which the driver starts moving the pedal, the foot from the accelerator pedal, transfer the foot to the braking one, and then press the brake. I said before that there are two models in the regulation. So you may wonder why we need a second model, why the CC model is not enough. Well, the fact is that the CC model is not capable of replicating a very important aspect of the human driving behavior, which is the anticipative behavior, the anticipation. As drivers, we are capable of anticipating events that happen while we are driving. For instance, we tend to react before a vehicle in front of us completely entered our trajectory. What does it mean? It means that if we understand that there is a vehicle in front of us that is performing a cut-in, we do not wait until the vehicle changes the lane, completely change the lane and cross the lane marking. But maybe if we can, we react before the vehicle, the cutting vehicle, cross the lane. This behavior, this anticipative behavior is captured, is replicated by this other model, the fuzzy safety model, the FSM. How this model is capable of replicating this anticipatory behavior through this condition. Because the real novelty of this model is the fact that the model is activated if this condition is valid. So if the time to the lateral time to collision is shorter than the longitudinal time to collision. And this condition can be valid, can happen even before the cutting in vehicle has already crossed the lane marking. This is how this model mimics the anticipatory behavior of a driver. Then this model introduces two fuzzy metrics for the longitudinal safety sec. And again, the model's outputs are two. Like in the Japanese models, in the CC model, the first output is the time instant when the driver, the human driver, starts reacting, so lifts the foot from the accelerator pedal to start the braking phase. And the second output is the braking profile. This time, another difference of the fuzzy model with respect to the CC one is that the braking profile of the fuzzy model is supposed to be more realistic than the CC model. Now, we have a regulation. We have two models, not one, but two models that define the collision boundary, to define the collision boundary of a competent and careful human driver. However, these models have limitations. The first limitation of this model is that the parameters they assume are deterministic. In particular, the parameters are not calibrated on observed outcomes. For instance, the collision on collision rates, which is in the end the main outcome of what we want to be the main outcome of the models. But their values are not those which produce the observed preventable, non-preventable boundary. They are assumed. For instance, the maximum acceleration assumed in the CC model is 6 meters per second squared, or the reaction time assumed in the CC model is 0.75 seconds. Now, you may wonder, why a maximum deceleration of 6 meters per second squared is assumed in the CC model, even if we all know that a driver can reach higher decelerations, especially in critical safety maneuvers. We can reach even deceleration even higher than 1G. So why 6 meters per second squared is assumed? You may also wonder why, for instance, 0.75 seconds is assumed as a reaction time, even if we know that there are drivers who can react faster with a shorter reaction time. Well, the fact is that whatever the assumptions behind these values, we should wonder what is the effect of these assumptions on the outcomes. Because are we sure that the outcomes resulting from these assumptions are valid and are capable of replicating the collision boundaries between preventable and unpreventable? Are we sure about this? Are we sure that the values that we decided are capable of doing that? Since we did not decide these values based on the observed preventable and preventable boundary. Well, it's clear that assuming, or even worse, negotiating the parameter values is methodologically wrong, and also is not transparent. What we should do is to decide the parameter values based on the reality, because the models should only replicate the reality. So these are the first general limitations of the models. There are also some model-specific limitations. For instance, for the CC model, the parameter values are assumed from distribution of heterogeneous drivers, so the average driver. But before we said that the goal is to reproduce the behavior of a competent and careful human driver, not the average driver. And also these distributions have been gathered via simulator experiment. As you can imagine, since the simulator is not the reality, there is an intrinsic error in the simulator coming data. Then another limit, let's say, but this is a limit related to the implementation of this model, is that in the open source implementation platform made available by the JRC, there are some biases. For instance, the lateral speed profile of the cut-in vehicle is like this, is a step function. while in the reality, a realistic lateral speed profile of a cutting-in vehicle is a parabolic speed profile. Or another bias is that in this implementation framework, simulation framework, the collision detection just recognizes the longitudinal collision, so the collision that happens like this. Instead, if the collision happens with the cutting-in vehicle hitting the side of the vehicle, the simulation framework does not detect this collision. So there are some biases. Given the situation, given the limits of the regulation and the outputs and the models of the regulation, what we did was to carry out an experimental campaign. We carried out an experimental campaign involving professional drivers, 10 professional drivers, because we said, okay, the goal of the regulation is to mimic the behavior of a competent and careful human driver, and we agreed on the fact that a professional driver can be reasonably assumed like to represent a competent and careful driver. So we went in Spain, in this test track in Spain, the middle of nowhere in Spain. We tested 10 professional drivers facing with cutting maneuvers, critical safety cutting maneuvers of different level of risk. In particular, we tested 2 different combinations of speed for the ego vehicle and the cutting-in vehicle, different lateral speed of the cutting-in vehicles, and different distances. So we made experiments. We said, okay, let's start from the data, from empirical data, and we collected them. These are just 2 videos to give you an idea of what the experimental campaign consisted in. This is an example of the maneuver, and this is the same maneuver from the inside. This is a professional driver, and these are the types of maneuvers we tested in this test track. Pure cut-ins, emergency cut-in. Just to give you an idea, again, about the experiments, for safety reasons, the cutting-in vehicle was not human-driven, was not driven by a human, but it was a robot, a cutting robot, and we were allowed to program the maneuver of this robot. The maneuver that we programmed was a realistic one, so the lateral speed profile of the robot was a parabolic one and not a step function. And this is an example of the experimental, the design of the experiments for 2 drivers. For instance, the first driver here started facing with a run with a cutting maneuver done with this characteristic. So at 60 meters, the cutting vehicles started the maneuver with a lateral speed of 0.8. This was the first run for the driver 1. The second one was this one with 50 meters as a longitudinal distance at 1.2, and then blah, 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 and then the rest of the experiments. Of course, the distance the design of the experiments was set before the experiments, but it was also adjusted based on the feedback coming from the drivers. The feedback was something like how difficult was the maneuvers that you just faced it with. So we collected data. We collected this data specific for emergency cut-in. We collected data involving 10 professional drivers, so what we think are competent and careful human drivers. And we used this data to validate the models proposed in the regulation. This is the flow. And this here in this slide is the main output of our campaign. So here what you can see are the results of the validation. First of all, let me say that you see 2 graphs, 2 plots, because as I said before, the experiments concern 2 different speed combinations for the ego, so for the vehicle driven by the professional drivers, and the cutting vehicle. The first combination was 60 and 10 kilometers per hour, the second 80 and 20. So 2 plots concerning the 2 combinations of speed. Then, for each graph on the x-axis, we have the longitudinal net spacing, so the net distance between the vehicle and the cutting-in vehicle when the maneuver started. On the y-axis, the cutting lateral speed peak, so the peak of the lateral speed of the cutting-in vehicle, and each dot in both the plots refer to a maneuver. So each dot refers to an experiment. Each dot concerns an experiment, a maneuver, a run. And the dots are colored according to the time to collision at the braking onset. As I said before, different combination of longitudinal distance and lateral speed result in different level of safety, level of risk. associated with the maneuver. How do we quantify the level of risk of the maneuver? We did through this measure, this time to collision at the braking onset. The braking onset is when the driver pressed the time to collision when the driver pressed the braking pedal. As you can imagine, the shorter is this quantity, the shorter is the time to collision, the higher is the level of risk of the maneuver. And indeed, as you can see, if we move to the left, this quantity becomes smaller. Why? Because, again, as you can imagine, if the maneuver starts when you are very close, when you have a vehicle very close in front of you, the level of safety, the level of risk increases. So if the longitudinal distance is short when the maneuver starts, we suppose, and indeed the data confirms that the level of risk is higher, and indeed the time at braking onset is shorter, and the points are colored here in purple, violet purple. That's the reason why we have also this pattern. So these are the points. The points represent the experiment. We have also axes. If you see, we have one X here, and another one here. The axis represent the evasive maneuver. As I said before, the idea of the models is to replicate, and also of the experiments is to replicate the behavior and study the behavior of the drivers while facing these cutting maneuvers. And the reaction is to decelerate, control the longitudinal dynamic of the vehicle to avoid the crash. In some cases, in particular in these three cases, the reaction of the driver was not only decelerate, but also to steer. So that's why we identify this maneuver as evasive maneuver, because there was not just the deceleration, but the steering. So these are the points, these are the X, the regions. Why we have these different colors? If you remember, the output of the models are the unpreventable and the preventable regions. So the unpreventable region is the region according which a competent driver is assumed to not avoid, is expected to not avoid the crash. The preventable region is the region for which we expect that the driver avoid the crash. The preventable, unpreventable region for the model CC, so for the CC model, is the yellow one, is this one. It continues also to the left. You cannot see very well because it overlaps with the other region, but I can assure that this region goes from here to here, from here to here. So according to the Japanese model, to the CC model, all the experiments falling into this region, this one, are experiments which are supposed to be unpreventable for a competent and careful human driver, which is not the case because we do not have the crash. So here, the collected data, so the empirical data, says that this experiment was not a crash. A human driver was able to prevent a crash, to avoid an accident in this case, while instead the model predicted a crash. So this is an output, this is the results. It confirms how inaccurate the model is. The red region instead is the fuzzy model collision region. Okay. Again, as for the CC model, also this region does not perfectly describe the data, what we observed, because, for instance, here we observed that for all these points, we did not have any crash. Instead, according to the CC model, a human driver cannot avoid a crash in these situations. So these results prove how unreliable are the models as they are. Plus, you may wonder also what this region, this green region means. I mean, usually green means good. Instead, in this case, it's not properly like this because the green region in this case means that there was no crash. The models did not predict a crash, just not because the models replicated the behavior of a driver who avoided the crash decelerating, but just because the models predicted no crash because the cutting vehicle was overtaken by the ego vehicle. So the ego vehicle did not decelerate at all, but overtook the cutting vehicle. So even if the models do not predict the crash for this safety, for this green region, they are still not accurate because they predict that the ego vehicle overtakes the cutting vehicle, which is a situation that we never faced with, we never had. So why the output of the models is so inaccurate? Why the models are not accurate? Well, the fact is that they are too conservative. Both the CC model and the fuzzy model, the CC model, especially CC model, are too conservative. So they classify as unpreventable events that in reality are easily handled by the humans. Why? The main problem is that both of the models make a mistake, make an error, when they identify the time when the driver has to react. So there is an incorrect identification of this time the time when the driver starts lifting the foot from the accelerator pedal and starts braking. This, for instance, is a slide in which we quantify the error. This error in identify the instant when the driver has to lift the foot from the accelerator pedal. This is the difference between the simulated time and the observed time, the time when the driver starts reacting. The simulated time, so these are the residuals, and for both models, the distribution lies to the right, saying that both models delay the reaction, especially the CC model, which lies to the right of the CC of the FSM region. This FSM is the distribution of this residual. This curve is the distribution of this residual when we simulate the FSM model. Instead, the blue curve is the residual distribution when we simulate the CC model. So when I say residual, it's the difference between the time simulated and the time observed. So what we are doing now, since we realize that these models are inaccurate, what we are doing is to developing a new model. In particular, we are developing a new model that is specific to emergency cut-in collision avoidance, and this designed based on empirical evidence. So what we did was we studied the models proposing the regulation. We validated the model against empirical data so that the models have show problem. And so now we are developing a model based on empirical data that we collected. In particular, what we are analyzing, what we are investigating is exactly the braking profile, the braking decision profile of the driver. Here, for instance, you have the speed profile of a driver during an experiment. This is just an example. This is an experiment in which the driver was at 60 kilometers per hour and then started decelerating to avoid the crash with the cut-in vehicle. And this is the speed profile, the lateral speed profile of the cut-in vehicle, the parabolic one. What we are doing is to analyze what are the causes, what are the factors that induced the reaction of the drivers. And here, this is the list of factors, the list of features that we are including in our analysis to develop this new model. In particular, these new features are, first of all, the lateral distance, this lateral distance, side-by-side distance between the two vehicles. This is the vehicle, this is the cut-in vehicle, and this is this distance, which affects, or may affect, but we included this in the list of variables that may affect the decision of this driver to react. If this distance becomes closer or shorter than a certain threshold, maybe this is the key feature that induces this vehicle, this driver, to react. Another feature that we are including in the model is the time to lane crossing, which is the time needed by this vehicle to cross the lane. The shorter this time, of course, the closer is the cut-in maneuver is about to happen, is about to be practical. Then a key novelty of the model that we are developing is this angle C, which is the angle between the vehicle, the cut-in vehicle, and the lane marking. This is a key novelty. Why? Because first of all, neither the CC and the FSM model consider the angle as a feature, as a variable to be considered when characterizing the reaction of a driver. So it's a novelty. And also, we know, even if you think about it when you drive, that basically our reaction is dictated, is influenced by the angle of the vehicles that is about to do the cut-in. Because if we see an angle like this, okay, so if we see that the vehicle is truly oriented to our lane, we started reacting. We are induced to react. We saw also that not only the angle is important, but also the variation, how this angle varies time. That's the reason why we also included this omega, which is the derivative of the angle with respect to the time, and also the omega dot, which is the derivative of the derivative of this angle. Then other two features that we included is the inverse time to collision, longitudinal time to collision, and inverse lateral time to collision. Just the last slide, I see an hand raised by Thomas, so I just finish. I just conclude with this slide, which are the first results of our model. What we did was to retrain and test the CC and the FSM model proposing the regulation based on the collected data. And these are the results of the retrained models with respect to the RMSF. And these are the results with respect to the RMSF of two models that we are developing. As you can see, the two models that we are developing, these two models differ from the features that are included. These two models perform better than the other two. And this is instead the error. This is instead the error that we have. As you can see, this is the distribution of the error, so not square, not raised. It's the normal error. And as you can see, both the models, the CC and the fuzzy, produce an error which is always above, almost always above zero. So they have a bias, a clear bias above zero, while instead the error produced by our model is centered to the zero. As you can see, the median of the distribution of the boxes is centered to the zero, saying that the model is not so biased, but is more reliable. And another evidence that the model that we are developing may be promising is that the dispersion of the output of the error is smaller than the dispersion of the error produced by these models, because the interquartile range of these two boxes is smaller compared to the interquartile ranges of these boxes. So that was my last slide. I give you back the floor to you, Galia.
Yes, many thanks, Giovanni. So we continue. I first thank you for the very detailed overview of your approach, of the methodology and the result presentation. So we continue now with our presentation. So Kranthi will share the screen. Okay, and so now we are presenting an alternative model for human driver. We are talking here about probabilistic situation awareness and safety maneuver prediction using the alternative modeling approach by dynamic Bayesian networks. So what, Kranthi, next one? Yes, maybe back. So who are the co-authors? So it is myself, Kranthi is my PhD student, and Professor Dr. Anders Madsen. We have been working on the modeling issues with Bayesian networks. And now we will show you how we proceed. We have proceeded and what data sets did we use for the modeling. Okay, so in the next, you see how did we come to this approach? Why is this important for the EU regulation? We had in the beginning of this project a meeting with the advisory board. This is the Joint Research Center with Biagio Chiufu and the Costa Mates, and they have told us about the safety approval of automated vehicles and the need to do validation and verification of developed model with the HIDE dataset. And based on this HIDE dataset, we are going also to show you the comparison between the models that are already integrated in the Joint Research Center simulator. And we will integrate our alternative model also inside to make comparison and to see how our model is performing in relation to the rest of those that are already integrated. Okay, Kranthi, next. Yes, so what is our generic approach following? So basically, we are having situation analysis where the human driver model is considering not only the sensor signals that we have in our availability to analyze the situation, but also considering the uncertainty of these data or sensor signals. in combination with the vehicle behavior, because the vehicle behavior we observe is basically expressing the way a human is steering this vehicle. So therefore, the combination of these are giving us kind of cognitive vehicle and automated driving systems that can profit from our model. And what exactly are we going to use in our approach to situation analysis? So basically, first question we ask is what automated driving tasks can be supported by such artificial cognitive systems like Bayesian networks, but also many other systems that are rising and part of state of the art. So basically, we want to cover the surrounding aware understanding of the driving scene and to have early recognition of highway maneuvers and situation criticality so that it is possible to pass this information to the car and have as early as possible preventive reaction for automated driving system. So basically, why is this possible? Because today's cars are equipped with many sensors. When I'm talking about the hypothesis, I will talk about also about the sensors and what is available today. But now I say a few words about the methodology and what models are we developing. So we will apply here Bayesian network for the development because we want to definitely integrate the knowledge about the problem domain and what we are learning from real data while driving on real roads. And then for maneuver recognition during this on-road driving, we are going to use these real data streams from real data on real roads, which represent a huge volume and have high frequency, 20 milliseconds, because we want to follow very quickly the change of the situation so that the car can react correspondingly and as early as possible. Therefore, we need prediction of the situation or of recognized maneuvers as early as possible. And why are we using Bayesian networks? Because we want a cognitive human driver model which allows us to mimic the human reasoning and to have a mimic process of how the decision of human is in the corresponding situation. Basically, how we decide as a human that a car in front of us is going to do a cut-in maneuver. So this is a pure situation analysis. So we want to deal, of course, with the inherited uncertainties in the automotive domain, since we measure many things, but this is never perfect. And of course, we want to explain the conclusions so that we as developer can also understand what is going on. And this can be also used for autonomous driving if we want to explain to the people sitting in the car what the car is doing right now. Okay, next. Yes, and see here you see what are the cognitive hypotheses for maneuver recognition that we are using and what are the features that we are combining into these cognitive hypotheses to mimic the human driving reasoning. And as I told you, I will here make the relation to what is available today and why with this model we are one step next than having a pure human driver. So if you look at the first hypothesis, this is what is the A is just telling you that we are using a symmetric coordinate system. This is just to simplify the recognition of maneuvers towards left or right, but the actual hypotheses are represented by B, C, and D. The B are the hypothesis, the features characterizing the hypothesis lateral movement or lateral evidence. So basically, we as a human, how we are recognizing that the car in front of us is going to do a lane change maneuver. If we see that the car is showing by its movement a kind of lateral speed component, so we see the car is moving towards the lane marking, and we see that the car is approaching closer and closer to the lane marking. So for us, is this a clear indication this car is intending to perform a lane change maneuver? The next hypothesis is the trajectory. So how do we recognize from the trajectory? This was also mentioned in the features of Giovanni used. So you see here the rotation of the car inside the lane, the time to lane crossing, and the acceleration observed. So these are features that are telling us as a human that a car is indeed going to perform a lane change, because otherwise it should drive just straight if it has no intention to change the lane. But if you observe rotation inside the lane, so this is obvious, it is intended lane change maneuver. And how do we know that this maneuver will be able to finish? If we see there is a free space on the neighbor lane, so the maneuver that is intended has also possibility to finish safely. And this is the so-called safety feature. So one of the safety feature is the lateral safety if we are going to finish the lane change maneuver. And the other safety is longitudinal safety. So if we're approaching a car with a speed that is much faster than the car in front of us, and if we know that usually in a highway we drive with a more or less constant speed, so if we want to keep this constant speed, so we need to change the lane in order to keep the constant speed that we are intending, because we have an obstacle, a slower driving car in front of us. And here comes to the moment why with this kind of cognitive model, we are having actually augmented human driver model. Because as a human, we are not able to measure all these features like what is the change of velocity, acceleration, lateral approach of the lane marking, time to lane crossing, and etc. So all these features are much easier to measure and to have really good accuracy if we are getting this from the sensors that are built in the car. Therefore, the driver sitting inside the car with this kind of features and software functionality is definitely augmented driver, because he's not handling the situation totally by himself, by own judgment, but it is having help to improve the entire perception of the situation and to be able to recognize lane change maneuver of neighboring cars, for example, as early as possible, so that the corresponding vehicle can react also as early as possible. Yes, then the next one. So this was the motivation. Why do we have augmented human driver if we are sitting in a modern car? And then, of course, a modern car has many sensors, but they are never perfect, like 100% measurement is exact. So we always have some kind of small deviation. So therefore, you see this signal as mu. This is the real value that is measured in the car. And in the normal deviation, you have a second parameter called S sigma squared. This is the standard deviation of the normally distributed measured signal. And therefore, for all measured signal, we can use the same modeling. And there you see that if we look at these free bubbles, they're representing a small fragment of the Bayesian network, where you have the real value is the really measured value. Sigma is the standard deviation of this signal, as measured is what we are getting as a measured distance. So therefore, we can base, you see this small e, this is the evidence of the measured signal. So we know what we are measuring, we know what is the accuracy of the sensor signal, and then we can deduce by inference what is the really measured value. So this is how we integrate the uncertainty in all measurements into our model. Okay, and next I show you how is this realized in a real car. So this is based on another project we had earlier. You see here the black car is a car that is driving faster than the truck in front. So therefore, if it wants to keep its speed, so it is changing the lanes. And here is the virtual representation of the situation. So you see the yellow arrow is showing the driving maneuver. So right now it was, can you repeat? Yes. Yes, so the yellow arrow was showing just the driving maneuver of following the lane. And if you see the blue one, this is showing that the car has, this we're just following the lane. The blue one says we need to change, the car in front of us needs to change the lane because there is a slower driving car in front. And we are aware of this since we are getting all this information, and we can react correspondingly as early as possible, corresponding to how many seconds did we recognize this maneuver earlier then it was performed. Yes, and from here we go to our real work in the i4Driving project. So what you have seen, these were the results from the i4Driving from the AMITS project. It was also European project, analysis of massive data streams, the analysis of massive data streams, and we are going to transfer now to calibrate this model that we were developing there as a cognitive car model. We are going to transfer it into the i4Driving project and calibrate it so that it becomes augmented human driving model. How are we going to do this? You see here on top is a figure that is representing the situation in the simulator, the JRC simulator, and you see that the features that are represented here are similar to the feature that we are using. We just need to calibrate the structure of the model so that it is representing basically the same feature. Why do we want to have exactly same features? Because we want to have comparability between the different models. So if you see what are the features used here we have on the side also the table. So we have the lateral velocity, this Vy, then we have the lateral distance between the two vehicles. If you look at our own models, we have also the lateral velocity. This is the red trajectory. It's showing already initiated maneuver here down. And the red trajectory is showing that the Kranthi down. Yes, so the red trajectory is showing that the car is initiating a maneuver. Why is it initiating in maneuver? Because the blue arrow is showing that the car is approaching a slower moving object 2 in front. Therefore, the object 1, if it wants to keep the speed, needs to do a lane change to the neighboring lane. And exactly these are the features that correspond to the feature used in the JRC simulator. And here I have just listed them, what is the analogy between the two models or the two approaches so that we have comparability at the end of our results. Yes, next. Yes, here's the acknowledgement of the videos that I have shown you from the i4Driving project and the cognitive human driver model. And then I pass to the next one. This is the heterogeneous augmented human driver model. As I already mentioned, what is our generic concept to situation analysis and cognitive model for maneuver recognition in order to be able to recognize the maneuver as early as possible so that we can react as early as possible. And then we can give some questions to these answers to these open research questions regarding augmented human driver model and uncertainties and what we are going, how are we going to realize this? This is the calibration of our cognitive hierarchical Bayesian network to augmented human driver model so that we can integrate it into the JRC simulator framework, and then we have the possibility to compare our model performance with all other models that were already integrated inside. So I pass now the floor to Kranthi, and we thank before that. I thank the Joint Research Center and the Smart Mobility team at the European Commission for introducing us to the regulation and for giving us this open research question and giving us access to the repository of code so that we can integrate the code of our model and have comparability between our model and the models that were already integrated. Okay, so now I pass to Kranthi and he can explain for you how we did calibrate our models so to have this comparability and what were the results of our models. Okay, Kranthi, so now it's your turn.
Sorry. Yes. So hi, hello everyone. Good afternoon. I'm Kranthi Kumar Talluri. I'm currently doing my PhD under Professor Dr. Galia Weidl. And this part of webinar, I'll discuss in detail about the modeling and integration strategy of our augmented human driver model. So I'll try to wrap up everything quickly because of the limited time. Okay. So As Professor Weidl earlier discussed, the motivation. So to this motivation, our approach is the Augmented Human Driver Model, which is a dynamic Debian dynamic Bayesian network based cognitive layer that enhances the human-like decision making. This Augmented Human Driver Model focuses on the safety, comfortable deceleration, and proactive response. Our main goal is to have the robust lane change intent prediction combined with safe reaction under uncertainty. So to evaluate our approach, we have integrated our Augmented Human Driver Model into JRC-FSM simulator, which is designed for safety validation, especially for critical cut-in scenarios as well. So the simulator already supports comparison of 4 baseline models, and each of the models in the simulator has 2 main modules, safety check and react. So our contribution was proposing the Augmented Human Driver Model with both safety check and react modeling, and then integrating into the JRC-FSM simulator for comparison with baseline models. So in this slide, we show you the fundamentals of a Bayesian network. So when the Bayesian network is extended over the time, it is called a dynamic Bayesian network. And this sample figure shows you how the Debian looks like. So unlike black box models, Debians allow us to understand why a decision was made, which is crucial in safety critical application. Now I will explain in detail about the Augmented Human Driver safety check modeling. So the Augmented Human Driver Safety Check module uses majorly 3 major hypotheses, probabilistic hypotheses. The first is lateral evidence for lane change intention, and lateral safety for lateral clearance assessment, and longitudinal safety for collision risk evaluation. So our modeling strategy was to design an augmented human driver, especially for safety check module, enhancing the competent and careful human driver safety check by integrating the lane change intention. So we want to integrate this lane change intention ability to competent and careful human driver model. So initially we use the existing competent and careful human driver model React logic for the vehicle to control to isolate the safety assessment improvement. So discussing about our first hypothesis, this is LE. It computes the probability of a lane change using the sigmoid function based on lateral velocity and the distance. It dynamically integrates the real-time matrices like lateral velocity, lateral distance, lateral acceleration, and all their uncertainties, providing an early hypothesis of lane change intent. When the cut-in vehicle moves laterally faster and closer to the ego lane, the belief in the lane change intent increases smoothly. So the scenario visualization shown here is about the ego vehicle, cut-in vehicle, and the matrices which are used in the modeling of this augmented human driver model. So the next hypothesis is safety assessment, which is performed parallelly in both the lateral and longitudinal directions. Longitudinal safety, which uses time to collision, relative speed, and longitudinal positions of both the vehicles. So based on these factors, it computes the probability that a collision might occur and determine whether the braking is required. Then we move to the lateral safety, safe lat. This evaluates the safety margin and check whether there is an sufficient lateral space considering the vehicle's width and position. Both augmented human driver model and competent and careful human driver model use the same react function. The key difference lies only in the safety assessment used to trigger the reaction. The augmented human driver model's capability to predict the intention of a cut-in 2 seconds early, which enables for more smooth braking and safe deceleration, while compared to CC human driver model fails to react in time due to no advanced safety check support that is resulting in a crash. So the key takeaway here is that augmented human driver model does not brake harder, it brakes earlier. The advantage of this predictive capabilities of augmented human driver model is illustrated in this comparison evaluation. Each point in this plot represent one simulated case of cut-in scenario defined by unique combination of longitudinal distance and lateral velocity. For this example, we considered ego speed is fixed to 90 kilometers per hour and continuous speed is fixed to 10 kilometers per hour. Why this combination? Because we want to consider the critical scenario to show the advantage of the modeling. And what we clearly observe from this plot is that FSM and RSS shows a moderate performance, while CC Human Driver and REG157 has the highest crash percentages. And whereas the Augmented Human Driver model avoids most of the crashes, causing only 124 crashes. And then quickly moving on to the performance evaluation, this table summarizes the overall crash performance across all simulated scenarios grouped into low speed and high speed. Low speed varying from 10 to 60 and high speed varying from 70 to 130 kilometers per hour. So what we see here is in low speed, RSS and FSM perform the best, whereas Augmented Human Driver remains competitive. Whereas in high speed scenarios, our Augmented Human Driver model clearly outperform all the other models. So this work is already published in IEEE IB conference. So to know more about the parameterization and modeling details, you can refer our paper. Link is also provided here. Then till now, as discussed earlier, every JRC FSM simulator model consists of two modules, safety check and react. Until now, I have presented the Augmented Human Driver safety check module and its results. And now in the next phase, I'll be presenting about the react modeling.
If you could do it, please, very quickly, Kranthi, because we are running out of time from the webinar.
Yes. Okay.
Thank
Yes,
you.
yes. So I'll quickly wrap up. As shown earlier, here we also do the performance evaluation of using Augmented Human Driver safety check module as well as React module. And we see that the number of crashes were earlier 124. And when we combine both the Augmented Human Driver aspects, the crashes are reduced to 100. So there is a clear improvement when we have both the modeling of probabilistic. And then here the similar way, we had the table of comparison where earlier settings, when we use the safety check of Augmented Human Driver and CC React, the crash percentages were 6.8 and 9.2. Whereas when we have both the probabilistic modeling of Augmented Safety Check and Augmented React, then the low speed and high speeds are very much crashes are reduced. So this is quite an improvement from previous setting. And so I'll conclude by saying that we developed Augmented Human Driver model using the dynamic Bayesian network for probabilistic safety assessment and vehicle reaction. Combining both probabilistic model proved to be advantageous due to early intent detection and robust safety assessment under uncertainty. And as well, this provides an explanation which helps in decision making. And yes, I would like to thank all our partners for their collaboration. And thank you, everyone. We are happy to take questions.
I saw a question in the chat. Thomas. So I think I can start from the first question, and then I will give you the floor to you, Galia and Kranthi. The first question is, can you explain a bit more on why different lateral speed profiles affect the model's output? Well, that's true. Very quickly, we said that there are two types of lateral speed profile. One is a step function. The other one is a parabolic speed profile. First of all, it's preferable to use this parabolic speed profile just because it's more realistic. Because usually we do not pass from 0 lateral speed to 1.8, 1.5. And instead, the other reason why it's preferable is because it changes the lateral speed profile changes the instant of activation of the models, especially the fuzzy model. If you remember, I will go very quickly. The fuzzy model has a first check, which is the time to collision check. If the lateral time to collision is lower than the longitudinal one, the model starts calculating the fuzzy safety matrix. Well, if you feed the model with the step function as a lateral speed, this inequality becomes true earlier, because you have a time to collision, a lateral time to collision, which is the lateral distance between the delta V, which becomes earlier very, very small, because you move from 0 to 1.8. While instead, if you feed the model with a parabolic speed profile, you have that this time to collision, lateral time to collision, has a proper course, has a proper profile. So that's the reason why. So it's better to use a parabolic speed profile. It should be. This is our first idea that we are testing. The second question is, can you expand on how the robot cutting maneuvers were programmed? Where just we selected the peak lateral speed that the robot had to reach, and longitudinal distance when the robot had to start the maneuver. That's it from my side.
Okay, then Kranthi, do you want to start?
You can say, Galia, quickly.
Okay, the question for us is, can you explain more on how augmented human driver will differ from regular human driver? That's a very nice question. Regular human driver, so you are completely alone in the car, so nobody is helping you while driving. This is if you look at the classification according to the law, so this is automation level 0, so you don't have any help through sensors. What we are talking about, the augmented human driver, this will correspond already to driving automation level 2 or even level 3. What is the difference to level 2 or level 3? Because the human is augmented with today available on the market software packages. So basically, if you buy today a car, so you can order a software package having functionality like safety package, where you have the lane keeping assistance, the blind spot monitoring, at ACC, so adaptive cruise control functionality, and other features like collision avoidance system. So these are all features that are helping the driver. Interesting is that 15 years ago, this was a feature available only in premium cars. If you look today on the market, you can just go in any house where the new cars are offered. So you will note that even mass-produced cars are offering as a serious functionality adaptive cruise control and blind spot monitoring, or even the lane keeping. So therefore, functionality that 15 years ago was like premium car functionality in the cars produced in the last maybe 2-3 years, is getting like a standard mass-produced car feature. And therefore, augmented human driver model is something that in the next years will get to be more and more observable on our everyday driving street. So basically, people do like to be a little bit supported while driving, because this is more relaxing situation. Yes, and then how did you integrate human behavior into the model? I can say about the hypothesis. We had hypotheses that are mimicking the human driving. I have already mentioned the lateral evidence hypothesis, or the lateral safety and longitudinal safety. This is also what Kranthi has calibrated into the new model, so that we can reproduce the same features that the JRC models are offering, and then we have comparability. Yes, about the market, I think I answered already what is available and what functionalities do the cars have. I said adaptive cruise control. 15 years ago, it was something great only for premium cars, and now almost every car that is new bought is available, is offering adaptive cruise control. So we are today in a much much better situation as a driver to have support in our everyday driving routines. Yes. Okay, and I see. Thank you both. Thank you too. Kranthi, do you want to say something?
No, it was very pleasure for us to participate in this webinar, and thank you so much.
Yes, and thank you also to Giovanni. Thanks.
Thanks to you, Galia. Thanks to you, Kranthi. Thanks to everyone.
Yes. Thank you.
Bye.
Bye-bye.
Thank you. Have a nice weekend.